Welcome back to the deep dive. If you are a software engineer or if you manage a team that writes software, I have a prediction for you. And it's not even really a prediction. It's more like a report from the field from late 2025.
Yeah.
Your job description has fundamentally changed. It is no longer about typing syntax. It's about architecting intelligence. We are so far past the era of the cute little autocomplete helper. This is a seismic enterprise-grade shift.
That's absolutely correct. I mean, the data we've compiled from our sources, all these analyses of elite engineering teams, the big tech platforms, it shows really without a doubt that AI is not just a tool for speeding things up anymore. It is redefining what enterprise-grade software creation even means.
Right. So for the engineer listening right now, you have to understand that the whole mental model has shifted.
It really has. We're moving away from thinking of AI as, computer-aided programming. That's an old idea. We're moving towards something entirely new. Agent-centric architecture.
So our mission today is to equip you, the learner, with that mental model for this new era. We're going to walk through the complete paradigm shift, the tech, the workflow, the governance, everything that enables this massive leap in velocity.
And we'll unpack the three big pillars that are holding this whole new ecosystem up. Context engineering, agent orchestration, and the unifying layer, what these teams are calling the Model Context Protocol, or MCP.
It sounds like it's about building an entire automated ecosystem that writes, tests, and even verifies code, not just, running a prompt in a chat window.
Exactly. When we talk about elite performance in 2025, we're talking about engineers who command a swarm of synthetic intelligence. And we're going to show you exactly how they're doing it and why the human role is, believe it or not, more critical than ever.
Okay, so let's unpack this idea of a fundamental phase transition. Our sources are all pointing to the back half of 2025 as the break point, the moment when, incremental improvement just became a foundational change. What exactly happened to trigger this? Was it one new model, or did the whole stack just mature at once?
It was the ecosystem maturing all at once, yeah, but with a few really critical breakthroughs. On the model side, you had the release of these truly frontier capabilities, specifically Google's Gemini 3 Pro and Anthropic's Claude Sonnet 4.5. These models just crossed key thresholds in reasoning and context handling.
But the models alone weren't enough, right?
No, not at all. They were coupled with the maturation of these agentic frameworks, things like Google Antigravity and the standardization that came from the Model Context Protocol.
So the interoperability was the key. It wasn't just having powerful engines. It was having engines that could actually talk to our databases, our infrastructure, and do it reliably.
Precisely. That combination ended what you might call the junior engineer phase of AI, where it was basically an intern. And it kicked off this new era of agent-centric architecture, which means the elite engineer's role is no longer writing the code. It's becoming this rigorous orchestrator of autonomous agents and, crucially, a highly skilled curator of the environment.
Of the context. Okay, so if the AI is writing 100% of the production code, which is what we're seeing in a lot of these benchmarks now, where does the human value come from? Is it just signing off on pull requests?
Oh, it's far more demanding than that. The human value now lives in two critical areas: the specification of intent and the verification of outcome. The engineer defines the parameters, the constraints, the business logic, the security requirements, all with surgical precision. Then they spend their time verifying that the outcome meets those specs perfectly, often by designing these really sophisticated test harnesses for the AI.
So they're not bogged down in the syntax anymore. They're designing the system at a conceptual level.
Exactly. And that shift in the core trade-off is what defines the elite engineer now.
This is where it gets really interesting because our sources indicate you can't just throw one big monolithic AI at this and expect good results. The elite teams, they don't treat AI as a single thing. They're doing what they call a strategic bifurcation of intelligence. They're deploying specific classes of models for specific cognitive tasks.
You have to. You absolutely have to, because not all intelligence is optimized for the same outcome. If you're building enterprise software, you need speed and you need correctness. You can't sacrifice one for the other. You wouldn't use a slow but perfect architect to manage a mass-scale file cleanup, and you wouldn't use a generalist for a critical piece of system design. You have to match the model to the cognitive load.
Okay, let's start with the heavy hitters then, the reasoning engines. We're talking about models like Claude Opus 4.5, maybe the hybrid Claude Sonnet 4.5. What's their main strength? Where do they fit in?
Their strength is pure precision and deductive reasoning. They're engineered for depth, for logical consistency. Think of them like a philosopher or a senior architect. The key architectural difference is their thinking paradigm. They can use this toggleable extended thinking, which is just a very sophisticated multi-step internal chain of thought process.
So they're basically writing out a detailed internal scratch pad before they commit to doing anything.
Exactly. And this lets them explore really complex concepts, trace data flow, restructure massive code bases, and verify all the logical paths before they emit a single line of code. It's slower, it's deliberate, it's highly rigorous, which makes them the ideal architects and reviewers. Now, their entire pattern is focused on correctness, not speed.
So if you have a complex refactoring job, or you need to make sure the billing logic is perfect, you call in the reasoning engine. But what's the trade-off? That extended thinking has to be expensive, right, in terms of latency and cost.
It is. It's very resource intensive. You pay a high compute and latency premium for that level of logical consistency. And that's why you reserve them for these high leverage tasks. If you use a reasoning engine to write a boilerplate React component, you're just burning money. And that calculation leads us right to the other class, the multimodal agent, things like Gemini 3 Pro and Flash. These are optimized for a completely different purpose.
Expansive intelligence, that sounds like they trade that depth for breadth.
Yeah.
Almost like a brilliant generalist who can synthesize huge amounts of data really, really quickly.
That's the perfect way to put it. They're optimized for massively parallel processing, for multimodal synthesis. And critically, we're talking about context windows now that exceed 2 million tokens.
Yeah.
Their ability to just ingest and process these vast amounts of data, it lets them perform what we call brute force auditing. They can scan an entire monolithic repository to find dependency breaks or security holes in minutes. They're the workhorses.
And the multimodal part means they're not just dealing with text and code, which must be a huge deal for front-end work.
Absolutely. They get used as builders and designers. They excel at synthesizing UI/UX from unstructured data, a rough video walkthrough, a sketch, a photo of a whiteboard. Their speed and their multimodal fluency make them perfect for rapid prototyping, for generating that first 90% of the code. They're the efficient background developer.
So this strategic divergence is really the heart of the new engineering practice. You choose your tool based on the cognitive load and the required fidelity. But that requires a big psychological shift from the engineer, right? You have to actually trust the machine to write the code.
It absolutely does. And the sources highlight this as the definitive end of the old not invented here syndrome. The elite engineers replace that with a curated by me philosophy. Their value is not from manually crafting syntax anymore. It's from the intellectual labor of specifying, verifying, and curating the AI's output. They're editing intent, not just text.
Which brings us to these fascinating new engineering personas that are emerging. First up, the compound engineer.
The compound engineer is the developer who manages that whole cycle. They use agents to write 100% of the production code, but, and this is the key, they maintain a complete surgical mental model of the entire system. Their skill set is system architecture, not language syntax. They use that precision to steer the AI, debugging and optimizing the generated code, often just by refining the prompt or context, not by fixing the code manually. And critically, they're achieving the output of a traditional 5-person squad, just through superior orchestration.
So they're leveraging the AI as a force multiplier, but without losing any control over the system. But then there's this even more extreme role, the 0.1x engineer. That sounds completely counterintuitive, someone who writes almost no code.
The 0.1x engineer is the ultimate leverage role. You can think of them as the editor-in-chief. They write a tiny amount of code personally, maybe 0.1x of the total code base, but their interventions have extremely high leverage. They spend their whole day pruning, curating, and refining the massive volumes of AI-generated code, focusing only on maintaining the conceptual integrity of the software.
So how do they fight the AI's tendency to be verbose or generic, the stuff that leads to code bloat and maintenance nightmares?
They fight it at the architecture level, at the constraint level. They don't review syntax, they're reviewing design patterns, dependency graphs. They might impose an explicit token budget on a task, forcing the AI to be concise. Their key job is making sure the system stays clean, scalable, and idiomatic. If an AI proposes a generic solution that needs a big, unnecessary library, the 0.1x engineer steps in and says, no, implement this with a standard library, even if it takes more steps. They are the ultimate system maintainers, the quality gatekeepers.
Okay, so if we accept that the engineer is now an orchestrator, their most important resource isn't the keyboard anymore, it's the context window. And the analogy our sources use is perfect. If the LLM is the CPU, the context window is the RAM. It's where the intelligence actually operates.
And that leads us directly to this new essential discipline, context engineering. The days of simple prompt engineering, crafting one clever query, are totally obsolete in the enterprise world. The goal of context engineering is to treat that context window as a finite, highly valuable, and architecturally critical resource, one that has to be managed for deterministic, enterprise-grade reliability.
So you're not just feeding it information, you're designing an entire temporary cognitive operating system for the AI to work inside of.
Exactly. The core idea here is that an agent's output must be a deterministic function of its input state. If you want that enterprise-grade reliability, if you want the agent to pass its unit test 99.9% of the time, you have to control that input state with engineering rigor. It moves beyond a fluid chat and into a systemic, version-controlled context paradigm.
And the best way to control that input state is through the context stack strategy. This layered approach seems foundational to how these teams work. Can you walk us through those layers?
Absolutely. The stratification matters because it manages the attention mechanism of the model. You have to present information in descending order of priority. So at the base, you've got the system prompt. This defines the agent's core identity, its immutable rules, its persona, security clearance, its whole philosophy.
That's like the long-term memory of the system.
It is. Then above that is the project context. This is the bulk of the engineering standards, the architecture, design patterns, coding conventions for this specific code base. Then you have the task context, which is the specific real-time requirements for the current job. The Jira ticket, the output format, the deadline.
And finally, the most volatile layer on top.
That's the dynamic context. This is all the real-time stuff retrieved documents, tool outputs from MCP servers like a database schema or a log file dump. It's highly transient, changing with every step the agent takes.
That stratification sounds like it directly addresses two huge risks from earlier LLM deployments: cost control and reliability.
It addresses both. First, context pollution, including irrelevant info dramatically increases latency, wastes compute, which means money, and it degrades the model's reasoning quality. If you feed the agent 2 million tokens and only half are relevant, the cost just balloons.
And you mentioned the lost in the middle phenomenon. How does layering combat that?
The lost in the middle phenomenon is where information buried deep inside a long, flat context window just gets ignored by the model. By carefully layering the stack, you make sure the most critical, high-leverage information, the system prompt, the project context, is always placed strategically at the beginning where the model is guaranteed to see it. It ensures core constraints are never violated.
To actually operationalize this level of control, teams have created a standardized instruction layer. They're embedding instructions right into the code base itself, which is, that's revolutionary.
Yes, through what they call instruction files. And these are not for humans. They are hidden markdown files, usually in special directories, that serve as the single, version-controlled source of truth for agent behavior. They're the operating manual for this synthetic intelligence. The main archetype here is the agent.md file. It's the project anchor.
Let's break down the structure of an elite agent.md. It has to be precise enough to guide an AI, but still flexible.
It's meticulously structured for a machine to parse. First, a clear role definition. This establishes a highly specific persona for the AI. For instance, you are a principal back-end engineer specializing in high concurrency Go systems. You are paranoid about memory leaks and value simplicity over complex design patterns. That sets the entire mental mode for the agent.
That specificity has to be key to getting quality code. And then you have the explicit rules of engagement.
Exactly. The directives, or the do's. These are explicit instructions like always prefer standard library NFTTP over third-party frameworks. And then crucially, the limitations, the don'ts, which prevent the most common failures. For example, do not modify go.mod without explicit permission. These hard constraints stop the agents from going rogue.
So this is the AI's rulebook. And the beauty is that this can scale up to huge monorepos through a hierarchical structure.
That's the core of how it's used in the enterprise. The root agents.md defines global standards, licensing rules, global security policies. But as the agent moves into a subdirectory, say microservice billing, it finds a nested agents.md with local conventions. In the billing service, use DynamoDB transactions exclusively. The agent automatically switches its mental mode based on its location in the file system.
On top of that, there are even more specialized rules for real-time steering, specifically the .cursor rules file for the IDE. How is this different from the agent.md?
The .cursor rules file is actively indexed by the Agentic IDE to steer code generation in real time at the moment the code is being written. It's like a real-time syntax and style guide. Think of agent.md as the design document and .cursor rules as the continuous linter.
Give us some concrete examples of what's in a .cursor rules file. What micro-level things are they enforcing?
Highly specific constraints. You see things like tech stack enforcement. When generating CSS, always use Tailwind classes. Never generate raw CSS. Import strategy is a big one for clean code bases. Use named exports with object parameters for all functions. Do not use default exports.
Yeah.
And perhaps most critically, safety guardrails. Do not run dev server commands. Ask me to execute the command. This fine-grained control prevents the agent from making dangerous unintended system calls.
It's almost like the AI is now wearing a straitjacket that the engineer designed for optimal performance.
It's a shift from flexibility to determinism. You trade a little flexibility for massive gains in reliability. Now, moving to advanced context optimization, the sources highlight these dynamic strategies for long-running tasks. The first is session splitting.
This sounds like it came directly out of the cost and latency problem with those big reasoning engines we talked about.
Absolutely. Session splitting is the practice of separating planning from implementation. The engineer starts a planning session with a verbose, expensive model like Opus 4.5. Its only job is to generate a highly detailed plan, which gets saved to a clean file, plan.md.
And then you immediately throw away that entire long, expensive reasoning history.
Exactly. You start a fresh, clean implementation session with a faster, coding-optimized model like Sonnet 4.5, and you load only the clean plan.md and the necessary code files. This prevents all the brainstorming and rejected ideas from polluting the context of the coding phase. It keeps the agent focused, efficient, and cost-effective.
That's really elegant resource management. And to maintain continuity, they use progress files.
Yes, often progress.md. The agent is instructed to append its current state, completed steps, and next actions to this file after every significant turn. This is its durable memory. If the context window fills or it crashes, the agent doesn't need a human to re-explain everything. It just reads progress.md and resumes work immediately. It's critical for reliability on long tasks.
And finally, to fight context pollution and its cost, they use context pruning.
This is an active human-steered step before the task even begins. The engineer tells the agent, read the file tree, identify the 5 most relevant files for this task, and ignore the rest. This active instruction forces the agent's attention onto the critical path. It drastically reduces the risk of hallucination by limiting the universe of facts it can draw from, forcing focus, and cutting the token cost.
Okay, so we've established that agents need context and constraints to be reliable. Now they need to interact with the real world, our internal APIs, our databases, our CI/CD pipelines. That used to be a huge headache of brittle custom integrations.
It was a massive point of friction. It prevented true enterprise autonomy. Every time a new LLM came out, you had to rewrite your entire tool ecosystem to talk to it. And that's why the Model Context Protocol, or MCP, is maybe the most significant infrastructure shift of late 2025. Our sources call it the USB-C for AI applications.
That USB-C analogy makes perfect sense. Build the connector once and anything can plug into it. It standardizes the communication layer.
Exactly. MCP functions on a standardized client-host-server architecture that decouples the AI model from the tools it uses. You have the MCP host, the agent runtime, like Claude Desktop, which knows how to speak MCP. It connects to the MCP server, which is a lightweight bridge, sitting next to a specific data source, like a database or a Jira instance. And the MCP client handles the protocol layer, facilitating secure communication.
And the genius here is the write once, run anywhere tool model.
It solves enterprise fragmentation overnight. Think about an internal tool. Before MCP, if you wanted Claude, Gemini, and an internal chatbot to use it, you needed 3 different custom API integrations. With MCP, the platform team builds one lightweight MCP server exposing their actions. Every agent, regardless of its model, can instantly plug into that server and start using the tools.
Let's get into some strategic uses then, starting with databases. The old, insecure way was just pasting SQL schemas into a chat window.
Totally unacceptable in an enterprise setting. Now, engineers run a database MCP server. The agent doesn't get the whole schema pasted in, which is a security risk and pollutes context. Instead, it uses MCP-enabled tools like getSchema to query the current state. And crucially, the server has strict rules, allowing the agent to run only safe, limited queries like select from users limit 5 to understand the data before it writes a migration script.
And this extends way beyond just data. It moves into infrastructure management.
Yes, and this is where automation gets really exciting. Companies are wrapping their existing microservices and deployment tools like Argo CD or Terraform in custom MCP servers. This lets agents interact directly with the infrastructure. An engineer can task an agent, check the deployment status of service X, And if the error rate is over 1%, revert the deployment. The agent interacts with the deployment infrastructure directly through that standard MCP layer.
Let's talk security integration. Autonomous security agents. That sounds like a huge leap forward.
It's a game changer because it integrates security at the agent level, not just the code level. Security teams use specialized servers like MCP Security Audit. They task the primary builder agent to generate the code, and then task a separate audit agent to autonomously crawl the local app and check it for OSP top 10 vulnerabilities.
So the agent itself is responsible for fuzzing its own code.
Precisely. The audit agent fuzzes endpoints, tests for SQL injection, and generates a report. This shifts security scanning from a post-commit CI/CD step, where fixing things is expensive, to a pre-commit agentic review step. It embeds security much, much earlier.
But maybe the most mind-bending example is in browser automation and end-to-end testing with the Playwright MCP server. This lets agents truly verify their own UI code autonomously.
This is what enables true autonomy in front-end development. The key difference is that the Playwright MCP server exposes the browser's accessibility tree to the agent, not just pixels or coordinates. Traditional browsing agents have to guess where a submit button is visually. It's incredibly brittle.
So instead of trying to click coordinate x500, y=300, the agent knows what the elements actually mean.
Exactly. The Playwright MCP server lets the agent interact semantically. It knows, for example, click the button with the role submit or find the input field labeled email. This semantic understanding lets the agent autonomously drive a browser, navigate to a page it just coded, and verify that the feature works as intended. It's performing autonomous E2E testing without any human supervision.
So we have the distributed intelligence, the structured context, and the universal connector. The last piece of the puzzle is the environment where the human operates. And the sources suggest that the traditional IDE is now secondary.
That's right. The traditional IDE was designed for a single user manually typing text. This new generation of tools is designed for orchestration. The focus shifts from the text editor to the agent manager, where the engineer spends most of their time monitoring and directing the fleet. This is the paradigm from platforms like Google Antigravity and Claude Code.
Let's start with Google Antigravity. Our sources call this the mission control paradigm. What does that interface actually look like?
Antigravity is an agent-first platform. The core interface is the manager view, where the developer is purely an architect, an air traffic controller. They spawn multiple asynchronous agents to work on parallel tasks. You might open 3 work streams. One agent assigned refactor the auth module, another update all public API docs, and a third generate 100% test coverage for the billing service.
And this is the magic of asynchronous orchestration. The agents are just working in the background, and the human is only monitoring.
Exactly, they're non-blocking. The human monitors the process on a task state dashboard, a live feed of what files are changing, which tests are passing. The human only steps in for high-level feedback, permissions, or plan corrections. You go from being the pilot of the code to being the commander of the whole squadron.
That high degree of parallelism sounds incredible, but it also raises a huge real-world question. How do they solve the trust problem, or the merge conflict nightmare?
That's a crucial point. The systems are designed to minimize this with file locking and separation of concerns. But the key mechanism for human trust and rapid approval is artifact-based verification. Instead of forcing the human to review hundreds of lines of raw code diffs, anti-gravity agents generate artifacts, tangible deliverables for review.
What kinds of artifacts are we talking about?
So if an agent is building a UI component, it generates a screenshot or a live preview artifact that the engineer can interact with right away. If it's a complex refactoring, it generates a detailed implementation plan artifact. The developer approves the artifact, the visible, verifiable outcome, which makes the review process way faster and more intuitive than reading raw code logs from a machine.
Now let's pivot to a very different approach, the one favored by terminal-loving engineers. Claude Code, the headless CLI-first approach.
Claude Code provides its intelligence directly in the shell, deeply integrated into the OS. This lets the agent execute standard CLI commands, grep, git status, to explore the codebase and verify the system state without a heavy GUI. It reads the output to understand the consequences of its actions.
And this is where the infamous risk-managed autonomy of YOLO mode comes in with the dangerously skip permissions flag.
Yes. And to be clear, the lead engineers never use this flag on their main production branch. It's strictly for sandboxed environments, disposable Docker containers, or throwaway Git worktree sessions. This mode just removes the friction of constantly asking for permission for every file edit or test run.
So what's the high-leverage scenario for YOLO mode?
It enables a fully autonomous workflow for massive repetitive tasks. You can give it a command like upgrade all dependencies, fix any breaking changes, and ensure all tests pass. The agent will just loop through the fix, test, and retry cycle until the job is done, without constant hand-holding. It saves so much time on tedious maintenance.
And this efficiency gets amplified by this squad of one strategy using Git worktree.
This is a direct application of that compound engineer concept.
Yeah.
Using Git worktree, a single engineer can spin up multiple isolated branches and run a separate Claude code agent session in each terminal tab, all at the same time. The human is now supervising 3 or 4 simultaneous autonomous development streams. The leverage is just massive.
And rounding out the IDEs, we have Project IDX, the cloud-native canvas powered by Gemini. What's its niche?
IDX is all about speed and multimodal input. It provides instantly configured cloud dev environments so you eliminate the works on my machine problem. Its unique strength, leveraging Gemini, is the app prototyping agent.
Tell us about the input. How do you feed it a design?
The input is high-bandwidth, unstructured data. An engineer takes a photo of a whiteboard sketch, a rough drawing, or even a narrated video walkthrough of what they want. The agent uses that visual input, along with configuration files like tailend.config.js, to generate a fully functional full-stack app, maybe next.js, plus Firebase in minutes. It's perfect for 0 to 1 development. #tag5, the elite workflow and enterprise governance.
All this speed and parallelism, it means the risk of producing faulty or insecure code is exponentially higher if the engineer isn't rigorous. So to make sure all this power doesn't just create chaos, elite teams are sticking to a very disciplined methodology. They use the Plan, Act, Reflect framework.
This framework is the human architect's way of imposing control and quality on the synthetic swarm. It makes sure the AI is solving problems rigorously, not just typing code fast. It mimics a senior human engineer's approach, but automated in 3 distinct phases.
Let's start with phase 1, the planning phase, the think step. This is where the human intervention is most valuable.
Absolutely. The objective here is defining what needs to be built and how it will be built before any production code is generated. You have to use a reasoning model Opus 4.5 or Gemini 3 Pro for its logical consistency. And the agent is explicitly forbidden from writing code. Its only output must be a rigorous version-controlled plan.md file.
What are the non-negotiable requirements for that plan.md? It can't just be a bullet list.
No, it has to be comprehensive, almost a mini-spec. It must detail the architecture, the file strategy, a precise list of files to be created or modified, a robust analysis of edge cases, and crucially, the verification strategy, detailing the necessary test cases.
And the sources all emphasize that the human review of this plan.md is the most critical intervention point. Why there?
Because correcting a flawed architecture in a text file takes seconds. But debugging a flawed implementation written across 20 files by an autonomous agent can take hours of human time. If the plan is sound, the resulting code is usually sound. The human architect's job has moved entirely upstream.
So once the plan is approved, we move to phase 2, the action phase, the build step, and you switch models here for speed.
Correct. Now you switch to a faster, cheaper coding model Sonnet 4.5 or Gemini 3 Flash for optimal speed. And the methodology becomes Agentic TDD, or test-driven development, but done autonomously.
Walk us through that Agentic TDD loop.
First, red. The agent reads the plan and writes a failing test case to confirm the feature doesn't exist yet. Second, green. It implements the minimum code needed to make that specific test pass. Third, refactor. Once it's green, the agent immediately refactors the code to meet the style guidelines in the .cursor rules file. This red-green refactor cycle loops autonomously until the whole plan is implemented.
And the final phase, for enterprise quality. Phase 3, the reflection phase, the verify step. This is where you bring in adversarial thinking.
This is the QA gate. The engineer spawns a separate, specialized agent, a reviewer agent or a security sub-agent. This new agent is totally separate from the one that wrote the code, and its prompt is highly adversarial. You are a senior security engineer. Review these changes. Look specifically for potential IDOR vulnerabilities, race conditions. The human only merges after this adversarial review is complete.
That level of rigor is what separates high-velocity AI coding from just chaotic output. Now let's go back to that concept of vibe coding for front-end work. This seems less structured than Plan, Act, Reflect.
It's structured by iteration and visual feedback. It relies on multimodal agents like Gemini 3 Pro. The input is highly unstructured, meant to capture human intent quickly, a whiteboard photo, a sketch, a narrated video. The engineer pairs this with config files, like the company's tailwind.config.js, to provide structure.
So the agent synthesizes the code from the visual input and the design system constraints.
Yes. But the real power is in the generative iteration. the image-to-code-to-image loop. The agent generates the initial code. The engineer takes a screenshot, draws a red circle on the misaligned button, and feeds that annotated screenshot back to the agent with a command. Fix this padding and make the shadow softer. The agent uses the visual error marker and the text command to instantly fix the code. It lets the engineer compile a vibe into production UI in seconds.
Shifting to enterprise scale, we have to talk about governance. When all your code is AI written, traceability becomes critical. This is where the AI Bill of Materials, AIBI, comes in.
The AI bomb is the new governance standard. Just like an SBOM tracks open source dependencies, the AI bomb tracks code provenance for compliance and traceability. It's an automated record appended to the commit history.
What are the key things tracked in this new standard?
It tracks several critical components. First, the model identity. Which model, what version? Second, the verification status. Which tests were run? What were the results? Third, and this is critical for security, the context snapshot. A hashed record to ensure no PII or secrets were accidentally leaked to the model. And finally, the human sign-off from the engineer who approved the merge.
The security patterns are fascinating because they treat the agent not as a trusted coworker, but like a temporary contractor with very limited access.
That's the core principle of least privilege for agents. A documentation agent only gets write access to the docs directory and read-only everywhere else. This strict containment prevents catastrophic fallout from a bad hallucination.
And they also use defensive subagents, or red teaming agents, as a formal part of the workflow.
Yes. These are specialized adversarial agents whose only job is to break the code written by the primary builder agent. They're designed to think maliciously. They fuzz API endpoints, try to inject malicious payloads. Only code that survives this autonomous red teaming gets presented to the human for final sign-off.
And for the highest risk actions where machine autonomy is just too dangerous, you still have human-in-the-loop gates.
This is the final safety net. Critical actions, deploying to production, modifying auth logic, changing database schemas, they trigger a mandatory validation gate. The agent is programmatically blocked until it gets an explicit, secure approval token from a human. The AI can propose the change, but it cannot execute it autonomously.
Finally, to optimize all of this, elite teams are rigorously measuring the output of their agent swarms. What are they tracking for AI velocity?
They track specific AI velocity metrics. The first is acceptance rate, the percentage of agent-generated code accepted without human changes. The target for elite teams is over 85%. Second is the intervention rate, how often the human has to stop the agent to correct a misunderstanding. The target is less than 1 per major task. And finally, context efficiency, which is tokens consumed per feature. That directly optimizes the compute cost and latency for the whole team. Hashtag clear outro.
We've covered a massive amount of ground, but the core takeaway is clear. The paradigm of software engineering has shifted, and it's not shifting back. The primary constraint on development is no longer the speed at which a human can type, but the speed at which a human can think, architect, and verify.
And that new era is enabled by those 3 pillars working together. We saw context engineering, which treats the AI's memory as a managed resource, the model context protocol, providing that universal, secure connectivity, and agentic IDEs like Antigravity and Claude Code, which transform the developer into mission control.
The future really belongs to the compound engineer, the system thinker who commands the swarm, orchestrating entire fleets of intelligence to build software at a scale we couldn't have imagined before.
Yes, exactly. The barrier to entry for writing code is completely collapsed. Syntax is now cheap, abundant, and easily generated. But the bar for architecting robust, secure, enterprise-grade systems has never been higher. So if English and context are the new programming languages, what skills should you be prioritizing right now? System design, threat modeling, domain-specific constraint specification to move from just being a developer to a true architect of intelligence. That is the strategic question you have to be asking yourself going into the new year.